Welcome to this Engineering Explainer. Look, if you're an aerospace engineer, a process manufacturing director, or you're overseeing high-precision component production, you already know the reality of our industry. The margin for error is virtually zero. Today, we're taking a highly professional, scientifically rigorous look at the exact tooling architectures engineered by Evergreen Carbide. We're going to see how they conquer the extreme thermal stress, the severe work hardening, and those unacceptable scrap rates that constantly plague complex aerospace component manufacturing.
To maximize our time, this explainer is structured into 4 precise phases. We have Section 1, the Superalloy Thermal Challenge. Section 2, PCBN and Advanced Tooling Tech. Section 3, Tolerance Preservation and Scrap Reduction. And finally, Section 4, Engineering Consultation.
Let's dive right into Section 1, the Superalloy Thermal Challenge, Material Hurdles in Aerospace Manufacturing. We have to start by addressing the destructive reality of cutting high-stress aerospace components. This is where thermal degradation leads directly to rapid tool failure and ultimately unacceptable part scrap rates. You know, aerospace manufacturing requires tooling engineered to conquer highly specific, extraordinarily tough materials. We're talking about nickel-based, cobalt, chromium, and iron-based high-temperature alloys, as well as hardened steels pushing Rockwell hardness scores of HRC 45 to 65. These simply aren't standard metals. Materials like Inconel and Aerospace-grade titanium are absolutely notorious for severe work hardening. When you machine them, they fight back. They can instantly degrade standard cutting edges and throw off even the tightest dimensional tolerances. And this right here perfectly illustrates the core of the problem. When processing these specific superalloys, the sheer friction and mechanical resistance generate immense heat. In fact, cutting temperatures at the localized tool workpiece interface can reach a punishing 1,300 degrees Celsius. To put that into perspective, at that temperature, standard carbide tooling literally softens. It undergoes plastic deformation and then it catastrophically fails. So, this extreme thermal stress poses a critical engineering question for us. At 1,300 degrees Celsius, how do we actually prevent this catastrophic tool degradation? How are we supposed to maintain the strict dimensional stability required for, say, an aerospace engine component without suffering from crippling scrap rates that just ruin production margins? That brings us to Section 2, PCB1 and Advanced Tooling Tech, High Heat Stability and Vibration Control. The answer to this massive thermal hurdle really lies in Evergreen's S-grade material technology. These polycrystalline cubic boron nitride, or PCBN, inserts are explicitly designed to maintain their extreme hardness and structural integrity even when things heat up to 1,300 degrees. This S-grade tech delivers superior wear resistance, alongside specialized variable helix designs that provide incredible vibration damping under really high load conditions. The PCBN material fundamentally resists the thermal softening that destroys conventional tools. It acts as a thermal shield, making sure your cutting edge stays sharp, rigid, and totally predictable when cutting hardened steels, powder metallurgy, or high-temp aerospace alloys. If we review the raw cutting parameters direct from the source data, you can see exactly how this PCBN tooling enables some seriously aggressive manufacturing. Just look at the parameters for hardened steel at or below HRC 55. For finishing and high-efficiency stable machining, we're comfortably pushing cutting speeds of 150 to 200 meters per minute with a 0.3 millimeter knifing depth. But check out the heavy cutting row. We're maintaining a speed of 80 meters per minute while taking a massive knifing depth of around 2.0 millimeters with a 0.2 feed rate. And when processing gray cast iron, those speeds can reach a staggering 1,200 meters per minute for high-efficiency finishing. These aren't just numbers on a spreadsheet. They represent massive reductions in cycle times while operating under immense continuous loads. But here's the crucial point. While PCBN provides that vital thermal shield and edge strength for aggressive roughing and heavy cutting, you can't stop there. The final, highly critical step in precision aerospace manufacturing requires a transition. To achieve those vital mirror finishes and exact geometric outlines, we must transition to advanced polycrystalline diamond, or PCD technology. By bridging the high heat resistance of the PCBN inserts with the ultra precision of the non-standard PCD milling cutters, we create a complete end-to-end tooling strategy. You use the PCBN to take the punishing heat of bulk material removal, and then you follow up with specialized PCD cutters to perfectly finish the complex product outlines where dimensional stability is absolutely paramount. It's a 1-2 punch. Let's take a closer look at these highly specialized tools. Evergreen's single-blade T-type milling cutters are engineered specifically for processing intricate inner cavity groove surfaces, which, as you know, is a really common feature in complex aerospace components. Meanwhile, The chamfer cutters are designed for flawless workpiece edge burr removal. By utilizing PCD material here, combined with superior vibration control in the tool body, your chamfering achieves a literal mirror effect. This completely eliminates the microscopic stress risers that can easily lead to a part failing in flight. Moving right along to Section 3, Tolerance Preservation and Scrap Reduction, maximizing floor-level efficiency. Now, how do these specific material technologies, PCBN and PCD, actually impact your bottom line on the shop floor? Well, compared to standard machining outcomes, which frequently result in rapid tool edge degradation, high dimensional drift, and a constant annoying need for machine stoppages and tool changeovers, Evergreen's integration tells a completely different story. Integrating PCD tools ensures that those complex aerospace outlines maintain incredibly tight tolerances. You get excellent dimensional stability and a mirror effect surface quality, all while exponentially extending the time between your tool changes. Direct from Evergreen's engineering documentation, this is really the defining metric. Excellent processing, dimensional stability, and surface quality, and the tool life can reach thousands to tens of thousands of pieces. This definitive capability right here is what allows process manufacturing directors to confidently scale up their high-precision component production. You're no longer sacrificing quality or losing valuable hours to constant retooling. You are effectively driving cost out of the process while pushing your quality up. Therefore, a rigorously optimized aerospace workflow follows this proven three-step sequence. Step 1. Thermal-resistant, aggressive, heavy roughing of superalloys utilizing our 1300-degree capable PCBN inserts. Step 2. Highly stable, vibration-damped, precision outline and inner cavity machining using our non-standard PCD T-type cutters. And finally, Step 3. Flawless, final edge burr removal with PCD chamfer putters to achieve a strict, aerospace-compliant mirror effect. And finally, Section 4. Engineering Consultation. Custom Machining Parameters. Look, every aerospace component is entirely unique, and applying these advanced tooling capabilities to your specific CNC programs requires precision planning. You can't just guess when you're cutting high-value superalloys. We formally invite aerospace engineers, CNC programmers, and process manufacturing directors to visit our technical hub at www.evergreencarbide.com. Reach out and request a custom machining parameter consultation. Our expert engineering team will work directly with you to develop customized cutting feeds, speeds, and tooling integrations tailored perfectly to your exact superalloy applications and specific machine tool dynamics. I want to leave you with this final, critical thought today. Before you initiate your next critical aerospace production run, take a hard look at your shop floor and ask yourself, is your current tooling strategy sacrificing dimensional stability and driving up expensive scrap rates when cutting at 1300 degrees? Because if you aren't absolutely certain that your tooling is engineered to survive the superalloy thermal challenge, it's definitely time to upgrade your approach. Thanks so much for joining me for this explainer, and we really look forward to engineering your next high-efficiency workflow.